Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning, everyone. I'm pleased to have Fredrik Kjolstad here. He's going to give his a talk about his work on Simit, which is my understanding is that it's a parallel language for graphics application. I know Fred from grad school back in UIUC, where he was doing his master's under supervision of Professor I forgot his Mark Sneer, and then he moved to MIT to do his PhD with Professor Saman Amarasinghe. Welcome.
Thanks, Saeed, and thanks for having me. So the stuff I'm going to be talking about today is collaboration with several other people. You got to catch them all. From different institutions. And a lot of these people are simulation researchers. They do simulation and optimization research. But there's also some compiler people in here. So we developed this new programming language called Simit that lets you compute on sparse systems. And it gives you convenience, and it also gives you performance. So there's many problems that involve computing on sparse systems, where most objects don't interact with most objects. Examples include meshes in physical simulation and geometry optimization, structured grids for fluid simulations, joins for robotics, and circuits for circuit simulations, and the World Wide Web or social networks for data analytics. You can also throw in Markov fields and base nets for machine learning. But let's take a closer look at mesh simulations first. So one of these simulations require you to think about two things at the same time. On the one hand, you have the behavior of your system. This is the laws of dynamics and motion. On the other hand, you have to think about the structure of your system. This is some discretized object that you want to simulate or compute the laws of motion on. The behavior is most easily expressed using linear algebra. And the structure is most easily expressed as some discretized object using a mesh data structure. But there's a wall between these two different abstractions, and it's a wall of performance and of productivity. So typically people get around this by having some loop that loops over their mesh data structure and inserts values into a sparse matrix. And then they can use an optimized sparse linear algebra library or Matlab calls to do the linear algebra itself. But this has productivity problems. Typically, you have to write some loop, and this loop has some really weird indexing that's really prone to off-by-one errors and other indexing errors. And it's also slow. These loops are not optimized unless you optimize them yourself, and they're not parallelized unless you parallelize them. And even if you do parallelize them, you have to have a reentrant linear algebra library, which is not common. The alternative is that you can rephrase your linear algebra as in-place computations on the mesh data structure. This is sometimes called a matrix-free computation. But now you have to write a lot of complicated code. If you want to run it on a different platform, such as a GPU or a distributed system, you have to write even more code. Let's look at a specific example. This is a neo-Hookean tetrahedral dynamics FEM simulation of this droopy dragon. Here we see a scatter plot of the performance productivity trade-off of some of the traditional choices for implementing this code. The x-axis shows source lines of code, and the y-axis shows the milliseconds per frame. So lower left is better. This is the trade-off frontier of traditional approaches. You can write your code in Matlab, which gives you good productivity. You don't have to write a lot of code, and the code is pretty readable. But the performance is lacking. Or you can go to somewhere in the middle, and you can write your code in C++, but use some optimized sparse linear algebra library, such as Eigen or PETSI. This gives you good performance, but you have to write some more code, and the code tends to become a little bit more complex. Or you can go to the other extreme, and you can hand optimize your code end-to-end as a matrix-free computation on the graph, the mesh data structure. But now you have to write a lot of code, but you get excellent performance. This is what the Sin et al. And the Vega developers did. Our goal is to get towards this lower left corner, which means few lines of code and also fast execution. So the Simit programming model lets you express both the structure and the behavior of your system in the same simulation loop. The behavior can be expressed as linear algebra just the way you like to do it. And the structure is represented as a hypergraph. A hypergraph is a generalization of a graph where edges can have any number of endpoints. So a normal graph would have 2 endpoints. The example we see here has 3 endpoints per edge. The edges are these squares, and the vertices are the circles. This hypergraph can represent a triangle mesh, where each triangle has 3 degrees of freedom. A key to Simit is what we call a vector or matrix assembly. It's a new programming language construct we developed that lets you go from one of these graphs, these hypergraphs, to matrices and vectors that you can then use to compute your behavior. And the indexing becomes pretty beautiful. It's much better than what you get with languages such as Matlab. So we believe this helps make Simit in some cases simpler to use than Matlab. And I'll get back to exactly why the indexing looks like that. And then the final thing you have to do is to close the simulation loop and write the results from your linear algebra computations back to your graph or mesh data structure. This program model compiles to CPUs, and it also compiles to GPUs with no changes to the program at all. So you get some portability there. So coming back to this performance productivity trade-off plot, Simit requires fewer lines of code than Matlab. And because of the simplified indexing, we also think those lines of code are simpler. But it gives you performance comparable or slightly better than Vega, which is hand-optimized code written by other researchers. And the same code also compiles to a GPU for about 9x more performance here. And now you're in the interactive realm. And you stay at the same source lines of code because you don't have to change your program to do it. So let's write some Simit code to get a feel for how this works and why this works. So let's simplify this dynamics code to a statics code and simplify the tetrahedra to these 6 triangles. So the first thing I need to do is I need to declare the hypergraph that represents these 6 triangles. I first create a vertex object. This is similar to a struct definition in a language like C. So this vertex object has degrees of freedom, it has position, it has velocity, and some external forces. Then I declare a set of these vertices. So here, just a set where you have one element per degree of freedom. Then I declare a triangle with some data as well. And then I declare a set of triangles. Now this set is an edge set, which means that each triangle in this set will connect 3 vertices from the vertex set. So now we have a graph consisting of these 2 sets. And I could declare other edge sets. I could have a pretty complicated graph with sets and edge sets and a lot of heterogeneity.
So what is the difference between a triangle and these squares that you created?
So the triangle is the geometric object. This square is the edge in Simit. Since Simit doesn't really know that this is a geometric object. For Simit, this is just a hypergraph. But since the user will use this to simulate geometry, for him it has meaning. So triangle is just a name of an edge. It could also have been a link, a web page link, if you wanted that. So now I've declared my hypergraph. And I want to do some computation. And the first computation I want to compute the area of each triangle as a pre-computation pass. And this is the code to do that. The compute area function on the top computes the area of a single triangle. It takes the triangle and it takes the degrees of freedom of that triangle as inputs. The init function has a statement called apply, which applies the compute area to each triangle in triangles. So you go through all of them and you compute their area. And this is similar to what you find in other graph processing frameworks such as GraphLab or its descendants, many descendants. The only difference here is that we support hypergraphs and somewhat more complicated graphs. But the real key to this is that we want to compute with linear algebra because that's often much more convenient. If you have a complicated application, you can get about 5 to 10x less code if you get to do that, as opposed to what you would have to write in this with these stencil applications.
So, two questions.
Yes.
So how do you specify? So that was a declaration of the graph, right?
Yeah.
How do you specify? Okay, this vertex is connected to this vertex. So that comes.
I'll describe that, but this is a C++ library with a language attached to it. So you would compile it just like you would compile a DirectX shader. And then you would run it on a data structure just like you would run the shader on a mesh. So in C++, you would initialize the graph and put the data in there. And then it
comes from an external data that tells you exactly how
that's
these
right.
are connected.
Yeah.
Question number 2, that is the source of parallelism, right? So you can compute these multiple of these areas.
Yeah, for these applies, these can be run in parallel, but linear algebra gets a different source of parallelism.
Oh, okay.
Because most of your application is not going to be this, because this is really convenient for simple stuff like this. If you want to do anything really complicated, where there's a lot of interaction between objects, you want to go to linear algebra really quickly.
Okay.
But the linear algebra is parallel too, inherently. To show how to use linear algebra, I'm going to write a Newton method. And this is the skeleton of the Newton method. There's a while loop that iterates until convergence. And then we're going to fill in some code to assemble a stiffness matrix that describes the sort of resistance the system has to being pushed together, compressed or expanded. A force vector, we're going to assemble a force vector, and we're going to compute a new position. So these vectors are going to be system matrices or global matrices. So they're going to have a size proportional to the size of your system. So very big sparse matrices. So we put that in place. So I said earlier that a key to all of this is this assembly construct that maps a graph to a matrix. And this is the assembly construct. So you have this map that maps the triangles. So it maps the triangles from that graph to this global matrix. And this statement works as follows. It applies this function here to every triangle in triangles, just like the apply did, the stencil did. But instead of just computing in place, it's going to return our global matrix. So each of these applications is going to return a global matrix with a few entries, and they're going to be summed together to give you the stiffness matrix of the whole system. So the way this process works is very integrated with how the type system of these dimensions of this matrix relate back to the graph. So to show how that works, I'm going to name all the vertices of the graph V1 through V7. And the vertices are the dimensions of the matrix. And if you think about what's going on, what this matrix does, what it means, is that it encodes some interaction between the vertices through these triangles, or through these edges. And instead of mapping the dimensions of the matrix, the entries of the matrix, to some arbitrary integers and indexing by those, we just let you index by the vertices themselves. So if you have one vertex, you can access one location in the matrix. If you have two vertices, you can access 4 locations in the matrix. And I'm going to show you now how this works to compute the stiffness contribution of a single triangle. So here's the code for computing the triangle stiffness of one triangle. So first we compute a 3x3 stiffness matrix. Notice that the type system of this global matrix has 3x3 inner blocks. This is useful because often you simulate something in R3 or R2 and you get these blocks. And look how simple it is to assign a 3x3 block into the global matrix. When you index into that matrix, you're indexing into a 3x3 block, and then you can just write in the 3x3 block you just computed. I'm omitting this function because this is just 3x3 linear algebra, and it's not essential to the rest, but it's a pretty straightforward function. When I compute this function for a single triangle, I can only write into 9 locations in in the matrix because the triangle has 3 degrees of freedom, and the combination of 3 with 3, the set combination is 9. But these are the only locations I need to write into the matrix, because the impact of this triangle is only the interaction it creates between those 3 vertices. Then the apply statement applies that triangle stiffness function to every triangle in your system, and you gradually build up your global matrix. And this is your global stiffness matrix.
Why do you need plus equal there? So why is not equal enough? Because you already specified that reduced
Yeah, it's true.
plus.
Equal is enough. It's just sometimes you want to increment inside your function. Sometimes you write twice inside this function.
But in this case, it's not necessary.
In this case, equals would be enough.
Yeah, okay.
Right now, in our implementation, what I want to do is I want to require plus equals just because then we don't. It's just an implementation detail why I want to require that. But
is it really true that when you did your simulation, some of the system matrices were within the same location, but they were being shared?
But they do.
So that's when you do a reduction of some sort.
But say
You had that notation there. Yeah.
So the semantics here is that you each of these compute one of these, and then you have, say, 1 million of these global stiffness matrices, and then you add them together here. So he's right that this is the thing that describes how you add them together. The other reduced plus inside the body there simply describes what's happening locally inside this application. Okay. So now you have the stiffness matrix that describes the interaction of all the triangles. So all the vertices with all the vertices through all the triangles. So now we have that.
So why did you have to pass t to this function? Just 3 vertices should have been sufficient, right?
Often you need some data from the triangle. So the triangle will have some mass. Typically you store mass on the triangle.
Okay.
So that's the reason. So this computation takes the t in and it uses t to do the computation.
So this matrix, okay, this is the computation phase, right? This is iteratively gets computed and
So it builds this. The computation comes after.
this.
It builds this matrix.
I thought this is built like beforehand. So
The graph is built beforehand.
Yeah.
The matrix is built.
the matrix is dynamically being built, or
No, it's not. But that's a compiler.
that's what I
compiler
want to
issue.
do. Okay.
We do pre-allocate memory for these matrices.
Right, but you don't know that, what the structure would be until you execute one of these functions.
No, you do, because the structure of this matrix relates to the graph. Because you can only write into these 9 locations.
Got it.
So the non-zero structure here of this particular matrix is exactly the graph structure.
So do you actually explicitly create this matrix, or is it implicit?
Right now, we pre-allocate the indices. We do explicitly materialize this matrix. We have a prototype of optimization that would take this whole assembly and the following linear algebra and push it back onto the graph so that we would have it completely matrix-free. So what that means is that the second you compute one of these 3x3 blocks, you immediately multiply it by the vector and get the contribution. So you never have to materialize this matrix. That's not implemented in the production line, but we have a prototype of that. So this gives us the stiffness matrix, and then we do the same for the force vector. The computation is equivalent, so I'm not going to go into it. And now we have the stiffness matrix and the force vector, and we need to compute the new position, and that's just 1 line of code. I solve a linear system to compute my position displacement. I add that together with the position at the beginning of my time step, and then I store it back to the vertex set. So notice that I can index a set and index the field of a set. What I get is a global vector that's a concatenation of the field from each vertex element. And this will have the same type as the dimension of the matrix. So I can add them together or multiply them together. And now I have a static FEM simulation. And this is all I need to do. But there's also Saeed asked me a while ago how this works, how I build the graph and how this works together with other code. So you don't want to rewrite all your code in a new language. So the way we solve it is that we made Simit a C++ library. And the way that looks is like this. So, so the design is similar to DirectX. Instead of meshes, you have graphs. Instead of shaders, you have Simit programs. So to use it, I declare a graph. I initialize the graph, and then I load, compile, and run the Newton method on that graph. And once I've executed this run once, I've done one time step. If I execute this in a loop, I do many time steps. So the performance of this comes from its design. There's at the moment, in the stuff we showed, this stuff I'm going to show in the results here, there's not too much extremely aggressive compile optimization. It's mostly things we almost get for free from this programming model. So what we do is that we pre-compute the indices of all the matrices because they relate back to the graph structure. I'll show a little bit after this slide, showing how that works when you start to multiply matrices with each other and add matrices together, because now the index structure of the matrix is going to start changing away from the graph, but it's still going to be a function of the graph. So we pre-assemble these, and this is key to performance. If you don't do this, you're going to have pretty poor performance. You can't allocate memory in the middle of a time step.
So if you multiply two matrices together in the middle of your computation, so there goes a new structure.
New structure.
So you have to dynamically allocate it.
No, we pre-compute that structure too. I'll show you in the next slide.
Okay.
We can trace how, because the new matrix you get from multiplying those matrices is still a function of the graph. It's just a more complicated function of the graph.
It's dynamically. You don't know how many iterations it's going to multiply that matrix.
If it's in a loop,
yes.
you either have to assume it's multiplied infinitely. That might give you a dense matrix, but sometimes it doesn't.
Right.
And I'll show you why.
Okay.
But if it goes into a loop, which is often doesn't, then you can lose track. And then you just have to do it dynamically.
So like at compile time, you figure out whether.
Yeah.
Okay.
If it's not in a loop, which is the common case, you know it. The second thing, oh, I'm sorry.
Yeah, I was wondering, this setup you showed for this hypergraph with three cliques, basically the
3 degrees.
3 degrees.
Endpoints, yeah.
But if your graph had mixture of different degree edges, is it going to become complicated, or is it just that the inner function which took the 3 by 3, that block size now becomes adaptive?
So we don't support a single edge set that has dynamic degrees at the moment. That's something we thought about adding. This is going to be more dynamic, much more dynamic. But what you can do is that if you have, say, triangles, but you also have some binary edges, you can have 2 edge sets. You assemble one matrix from each, and then you add them together. That's something you can do. We do support having any number of edge sets, and edges can even connect other edges, so you get topology. But we don't support, at the moment, the one edge set with dynamic number of...
I see. But you would probably know beforehand what, like you said, they would have triangles and single edges, so that way you can actually combine the 2 edge sets and do what you need.
Yeah, you just 2 matrices, add them together, and then you go. Like one common case is that you have, say, triangles, but then you also have some constraints, maybe Dirichlet constraints, or some collision is constraint between this mesh and that mesh. You can encode the Dirichlet constraint is just edges with a single endpoint, and the collision constraints would just be another edge set with edges with 2 endpoints. And then you can assemble a matrix from that, and that would be your collision resolution matrix. And then you can use them together, because the dimensions will be the same, it's just the structure will be different. So type check. So also, because we had this blocked linear algebra type system, we do blocked linear algebra. We emit code to do blocked linear algebra. So you, in the kernel of the sparse linear algebra loops, we just do dense linear algebra. That gives us more performance. And the last thing we do some fusion. So if you want to add 3 vectors together with libraries, you typically add the first 2 vectors into a temporary, and then you add that vector to a third. What we do is that we fuse it together, so you add the 3 first elements, and then the 3 second. Yes.
So in all of your examples of linear algebra, you've always had a sparse matrix and a dense vector. Just pictorially, I'm just curious, is that also what you've seen in applications? Have you ever had a sparse vector and sparse matrix?
We haven't. We've been developing a compiler theory, which we'll touch on a little bit, that can deal with things like that. But we don't see that in physical simulation. Well, it's not quite true. We have seen that a little bit in physical simulation. It's just we don't support it in the language. Well, in the compiler, I mean.
And how big are these matrices? How many dimensions?
You
Number, like hundreds, thousands?
Rows and columns?
Rows and
It just depends on the size of your system. We can, in physical simulation, you can make the dragon as discretized as you want. So our dragon was 160,000.
160,000.
160,000 tetrahedra.
Wow. Okay.
And that's not too big.
That's not too big.
And you're inverting a matrix of that, a sparse version of that matrix?
Conjugate gradient method, yeah. Yeah.
Yeah, 2 millions.
Yeah, we do that in way less than a second.
Yeah.
It's a conjugate gradient method, and since this is graphics, we don't need it to fully converge.
Yeah.
They can stop it whenever it looks good.
Right.
Yeah. But that cloth I showed has 1 million edges.
Wow, okay.
And it has 2 edge sets because it's a discrete shell simulation, so it has triangles, but also hinges between pairs of triangles that prevents it from bending.
So one example to the case that Todd was getting to, when the sparse vector is important, is like, for example, graph algebra, like single social stat problem, when you don't want to consider all of the vertices for the next update. You know, is the case that.
I believe Charit Mendes was working on that last summer here at Sparse, and he's been telling me about because we're in the same group.
Yes.
But I've also seen it in physics, where you sometimes want a matrix where each column is just going to have 3 values, and you use that to sort of slice out of a vector. So it's important with sparse vectors. It's just, for a lot of physical simulation, it's slightly less important than the dense vector. We also done some stuff on much more aggressive fusion. We're developing this compiler here for much more aggressive fusion, where you can start to fuse sparse structures too, not just dense structures. So we talked about the indices of the matrices. So we have this thing we call a path expression that describes the structure of a matrix symbolically. And the way that works is that when you assemble a matrix, you get a path expression like this. This is a system with 4 degrees of freedom and 3 edges. When I assemble a matrix, I get a path expression that describes for each row. The non-zeros on that row are your neighbors through an edge. If I multiply that matrix by itself, I get this path. So I can jump from a vertex to an edge, back to the vertex, back to the edge, to the next. Or I can jump 2 hops out. So you get it becomes a breadth first search. When I keep multiplying it, it sort of grows out, which is what you see in this graph algorithms influence linear algebra. So where this becomes more interesting is when you have a more heterogeneous system. So here you have 2 sets that are connected by edges. So these edges are heterogeneous. One of the endpoint is green, and the other one is purple. And the matrices you get are rectangular. So this is sort of where rectangular matrices come from. I get 2 different. So the first matrix goes from a vertex through an edge to that, and the other one is the reverse. If I multiply those 2 matrices together, so AAT, I get this thing where I first have to jump through an edge to a purple, and then to a green. And you can see it gets this funky structure. And when I multiply the matrix the other way around, I get this bigger one. And if I keep multiplying it, I end at this, and this structure is stable. These are never going to fill in.
But this path expression is not unique to the matrices, right? Meaning that for one path expressions, there are multiple matrices that match that expression.
Yes, so we compute the indices for all of those matrices once, and they use the same index.
Okay.
We don't compute one for every matrix. We do a memorization there, which is important because often you assemble 2 from the same edge set, and they're the same. You want to add them together.
From the path expression, you can tell me what sparsity it would look like in the matrix.
Yeah, if I have the graph and the path expression, I can combine them and compute something we call a path index. And now I materialize the structure of the matrix. And it's cool. So if you have 2 matrices with the same path expression and you add them together, you can do that really quickly because you just add them as 2 vectors. And the final thing is if I have 2 different edges. So I have 1 vertex set with 2 edges. I get these 2 matrices. When I multiply them together, several times, end up in a stable configuration. And the reason why these two are not filled in, so the first column is not filled in because I have to jump through a purple edge first. And there's no way to get from V1 through a purple edge anywhere, so you're stuck. And the same goes the other way. There's no way to get through to V4 through a blue edge. So we can have some sparsity even if it's in a loop. So getting to some results. I'm going to show some results for these three applications. Oh, yes.
So when you materialize those matrices,
Mm-hmm.
So I guess it depends on like the sparsity of the matrix that you decide how you lay out the data, right?
Oh, yeah.
And like how, so do you have like different representation for like different sparsity of these matrices?
Right now we make all of them blocked compressed sparse row, or blocked compressed sparse column. The compile theory I alluded to allows you to have different sparsities. Like you can have alpac, which makes a lot of sense if every matrix every row has the same number of non-zeros. You can skip one of the two arrays, the index arrays, and you can essentially you compute locations in the output matrix. Alpac is important. Dia is another really important one where your matrix comes from a structured grid. So you can actually compute all the locations. You don't need any indexes at all. But in our current implementation, we just use block compressed sparse row, which works pretty well, and it's general. But alpac is important. Alpac, the one where you assume they have the same number of non-zeros on each row, that's a pretty common case because you have two classes of graphs like it seems everywhere. So either it's graphs with high diameter and a bounded number of a bounded degree on each vertex, and those you find in physical systems because physics is local. For those things, alpac works pretty well because say this dragon has on average 10 out degrees per vertex. And the distribution is goes from 6 to about 12. So you can just assume everyone has 12, and then you can have a pretty compact index. But then you have the other graphs, the parallel graphs, that you get from social networks and web pages, and there alpac would just fall on its face. So on this slide, I show we see the lines of code it took to implement these three codes. So it's the FEM dragon code, sorry, I jumped over that slide. So there's an FEM dragon code. There's a mass spring system on this bunny. And then there's this discrete shell simulation I talked about a little bit. So here's the lines of code it took to implement them in Simit. And here's the lines of code it took to implement them with these other approaches. Some of these were implemented by my collaborators, and some of them were implemented by other researchers outside of our group. So, but the ones implemented by the collaborators, some of those were implemented before we started this work. And in all cases, the Simit programs are shorter. And because of the simplified indexing, we also think it's simpler. Here's the runtime of Simit running on a CPU with double precision on each of the three codes. And here's the runtime of alternatives. Simit is faster in all cases, except when compared to Eigen for this class code. And the reason for that is that the Eigen library, sparse linear algebra library, vectorizes dense 3x3 operations. And those dense 3x3 operations dominate this code because it's an explicit code, so there's no solver in it. And the matrix assembly dominates the performance.
Why not using just MKL, for example? For
to compare with?
No, just to do those block.
Oh, we didn't focus on it yet. We want to add vectorization for sure, so that we get that performance too.
So you don't have to worry about it in that sense. So you just call MKL and it does the right thing for you.
Yeah, so MKL is might not be the best for small 3x3 operations.
Oh, these are super tiny.
Eigen runs a lot of template tricks to make that really fast.
Got it.
So it's really a template compiler. So we also want to vectorize to get that, but instead we support GPUs. And on GPUs you get 5 to 10x more performance, and now you're way ahead of Eigen.
I see.
So on the CPU, you haven't used vectorization at all?
No vectorization.
So now I see why you are using double precision. If you were using single precision, then the vectorization would, accumulate more operations
I see. Well, that's not the reason we use double precision. We always want to use double precision. It's just we don't support it on the GPU. Yeah. That's why we use single precision here. Otherwise, we would use it across the board. I don't know the performance difference. I think the performance, it's just like you get 10% faster in both cases. Oh, okay. It's not that huge of a difference. But when you get to the GPU, you're way ahead anyway. Yeah. So we don't parallelize the CPU version either yet. We haven't gotten there. Oh. But we have no reason to believe that it's sequential, yeah. Okay. But the other ones are also sequential, because when you have a sparse linear algebra library, it doesn't make too much sense to parallelize it because the other part of the computation is not parallelized. And that's what happens here. Look here. So this is, we implemented this FEM code using the QSparse library from NVIDIA. And that's a really fast sparse linear algebra library on the GPU. But but if you assemble your matrix without writing that code for the GPU, if you assemble it the way that's most convenient on the CPU, and then transfer the data, you get really poor performance. So this shows that even though you have part of your computation really fast, if the rest is not fast as well, you're going to suffer. But with Simit, just everything compiles to a GPU, and you don't get that hit. Yeah. Of course, if we manually implemented assembly on the GPU, we would get comparable performance, maybe even a little better, depending on how much time is spent optimizing that. These show the importance of running it on the having a portable programming model. Top row is Simit running on the CPU, bottom is Simit running on the GPU. So modern programming models have to be portable because modern machines are diverse. So we've only scratched the surface of the kind of optimizations we think we can do. For instance, I mentioned we don't vectorize yet. I mentioned that we do some fusion and some matrix-free in the sense that we pre-compute indices, but we don't do the matrix-free that was asked for. We're working on that. We're working on much more aggressive fusion where we fuse through sparse matrices too. We want to add vectorization, we want to add multi-threading, and we want to run Simit programs on distributed systems. And we strongly believe that the abstractions we have can let you do that without the Simit programs changing. So the programs as written today will later run on a supercomputer with 0 changes. And the reason why we think this will work is that we have the same property in Simit programs as the relational algebra has and that Halide has, which is a Simit program doesn't encode any information about where things are placed in memory or the order things are accessed in. And Edward Codd called this property, the relational algebra guy, called this property physical data independence. And in the paper where he describes relational algebra, he describes that algebra because he wants this property. We have the same property because we also don't encode that information into the programs. So Michael Stonebreaker, in a paper he wrote called "What Goes Around Comes Around," describes why you have in a programming model where you want data independence, you have to have a collection, and you have to compute on that collection as a whole. You can't compute one piece at a time. He describes why that's essential for data processing, and we believe that's equally essential for computational programming models, because without a collection-oriented approach and operation on the collection as a whole, such as linear algebra, such as the database join, you break the data, the physical data independence property, and you can't do all of these things without the user programs changing. So Sippelstein and Blalock, in a 1991 paper called Collection-Oriented Programming Languages, describe a host of these type of languages that operate on collections. Simit is a collection-oriented programming language. We work on collections. We have 2 collections. We have graphs, and we also have the matrices. They're both collections. We have a way to move between them, so it's a little bit more diverse that way. But more precise than a collection-oriented language, it's a system-oriented language because you compute on systems, and you compute on the interaction between systems. And we think system-oriented programming language sort of inverts the idea with object orientation, because the way object orientation was designed by Alan Kay and those guys, those early guys, is that you have separate objects. Each object is a machine. That machine, it receives messages, it computes, it sends messages, but it works independent of the whole. When you have a bunch of these machines, you get emergent behavior. This is very biological inspired, which makes sense because Alan Kay was a biologist first. In Simit, we invert this. You compute on the system as a whole with these global matrices, and then the behavior of the individual pieces emerges from the behavior of the system. That makes less sense in some biology. It makes more sense for physics. So to show an example of how these abstractions can let us do stuff, this isn't stuff we've done yet, but this is sort of our idea for going to parallelism. We simply partition the graph, and then since the dimensions of the matrices are things on the graph, we just partition the matrices the same way. And then that's pretty much it. And it's a very simple idea, this idea of subgraphs and submatrices and subvectors. But it's simple, but it's pretty powerful. And it can also be used for cache blocking, so we can get a lot of bang for our buck that way. So I've been talking about physical simulations on the formables, but we think this idea of sparse system, this sparse system is personally in algebra, it applies much more broadly. It applies to structured grid computations, to some optimization like geometry optimizations and a lot of the least squares things, rigid bodies like joint systems, things like that, card houses and robot arms, networks, for instance, circuit simulations with a Boolean matrix, or machine learning and data analytics. We have implemented PageRank in Simit, for instance. So let's look at the structured grids quickly. Let's see how we're doing on time. Okay, we've focused on structured grid a bit, and we've been working together with some people in the theoretical physics department at MIT to implement lattice quantum chromodynamics in Simit. And we have the early implementations, but it requires some extensions to deal with this special case of graph, where you have coordinates. So this grid has coordinates, and you can use that to get more performance. And you also need to use it to describe your matrices. So in these kind of graphs, you have a grid like this. The reason why I drew it like this and not as an image is that sometimes you need to store things on the edges too. That's not important for it. Yes?
So, once you have structure, the Simit language begins to look more and more like halide. Is that true?
The matrix assemblies begin to look a lot like halide, but then you get the matrices and you can do linear algebra. And for a lot of the image filters, that doesn't buy you a whole lot, because matrix vector multiplication is just a halide filter. But for more complicated things where you want to do a solve, doing that in a stencil language starts to become very cumbersome. And if you have a more dynamic system where you have, say, this grid, but then you also have some mesh and they need to interact, say you have a Lagrangian thing moving in a fluid, you have to have both the unstructured and the structured thing in the same approach. And then if you don't have matrices, it's going to become very difficult to program it. So the matrices, what they really let you do, they let you hide all the details of your whole system inside one symbol. And then you compute with that symbol as if it's just one object moving in very high dimensional space. But our idea here is to compile Simit to halide, so there's that. So sort of Simit stops where halide starts. So here you have a stencil, but the Simit way is compute a matrix and then compute with that. And then let us handle fusing this matrix together with the matrix vector multiplications to get the performance of a stencil code. It's a compiler optimization for us. Here's the syntax of an assembly. You get the points in a stencil, and you also get the edges. And you can write to the point using these relative coordinates. We also let you index the edges, because you might have data on those. It's important in quantum chromodynamics. So now you index a vertex and another vertex, and now you index the edge between those two vertices. Then you can read data. So this edge, for instance, I would index first 10 and then 11, and then I get the data from that one. So this is work mostly done by Gurtei Kanwar, who just joined the theoretical physics department, so a PhD student, but he did a master in our group first. So he's both in CS and theoretical physics. It's pretty impressive. So let me quickly talk a little bit about optimization, just showing some stuff I've done this summer at Adobe. So when you have optimizations, you start to want to consider these constraints. So you have these edges, but you also have these constraint edges. So those could be a Dirichlet constraint, just say, pin this vertex here in space. Or they can be a collision constraint, saying these two things should not go past each other. Here you want to assemble more complicated matrices, like this KKT matrix, where this is your stiffness matrix we've been looking at. And these are also assembled matrices. So these are all three system matrices. And you sort of add these constraints on the side, and then you want to do a solve with that. So this is a set of Lagrange multipliers. So we've extended our type system to allow you to also have other sets than the set of the elements of a set in the types. And you also want to do things like Schur complements, which is just a fast way to compute this in certain cases. So we've added these sort of built-in functions to Simit. And if you're anything like me, these built-in functions make you very uncomfortable because like a Cholesky solve is a really big primitive. And which means we have a big runtime library that we have to port to GPUs and supercomputers. So we started to look at how to break these into language constructs that compose, that we can write Cholesky and then compile it to different machines. That would be that's actually the interesting thing about that is that thing in Simit is go from graph to matrices, but with these Choleskys you actually do the inverse. You go back to a graph, and then you do some graph operations on that graph, and you combine that with numerical optimization to solve a sparse Cholesky factorization. It's very interesting stuff. And then running out of time, so I'm going to just quickly show this. This is the PageRank implemented in Simit. Here you assemble your PageRank matrix, and then you get to compute PageRank using linear algebra, the way they described it in the original PageRank paper. The key to these kind of thing is that you have a parallel graph that I alluded to earlier. That's not important for describing the code, but it's really important for running the code. And the power graph stuff from Berkeley shows us that what you want to do is that you want to partition your graph by the edges and then replicate the vertices, because there's so many more edges than there are vertices.
So in this example, do you unroll iter times for the linear algebra kernel, or are you dynamically?
We dynamically go around that, but
I'm sorry, you go around it?
Yeah.
Okay. So it's dynamic?
This is a vector, so you don't compute an output structure. If this was a matrix, it would be dynamically allocated. Okay. Unless, so we don't do that at the moment, but unless you could detect that this int is a fixed number of time, and then you just create a big path expression, and you know the structure. So the final thing is that we're also looking at how to extend the stuff to tensor algebra, because vector and matrices are just a subcase of tensors. In our language, we support describing tensors, but we're still working on the compiler theory that lets us emit tensor algebra. That would be sparse tensor algebra. So the motivation for that is that the motivation for this new compiler theory that will deal with both sparse and dense linear algebra and sparse and dense tensor algebra is that you have all these invariants in libraries. Like in Eigen, you find this matrix vector multiplication. In C-sparse, you get to add the result back to the vector you started with. In PETC, you get to add it to a different vector. In ASCII, you get to scale both of these sides by a scalar. And the reason why they add these more compound kernels is that this is a common case, and you don't want to have to do this as binary operations with big temporaries. But of course, if you don't need to scale, setting these to ones gives you redundant computation. So that's why they add all these different variants. And then in PETC, you can also transpose your matrix, and you can transpose your matrix and add it to a vector. And this is just 3 libraries or 4 libraries, and that's 6 versions. And then you have different formats, which Mangpo mentioned. This is just the 4 most important ones, but there's 50 other ones that's not so important. So there's 4 formats, but you might want each of them blocked with dense blocked. You might want to have variable blocked, and you might want to doubly compress those 2 at the top to in case you have a system where there are a lot of rows or columns don't have any entries. And then you have different machine architectures, and you might want to sparse vectors. And if you want to add all the other compound expressions, now you have an infinite number of variants. And with the tensor algebra, even just binary expressions, since the tensors can have any order, is an infinite number of things. And you can't write an infinite amount of library code, so you need a compiler approach. And what we have is a compiler theory that lets you take any compound linear algebra expression, where the operands can be sparse or dense or a mix, and the sparsity can be different formats. And then we can generate code that iterates over the joint sparse iteration space of the whole expression and compute the whole expression in one pass. So we're finishing up, extending it to tensor algebra. The same theory generalizes, and preparing it for publication. And so before I conclude, so I've been talking about topology or structure and algebra, linear algebra. But there's a third piece we don't support in Simit, and that's geometry. So you could have the geometry of an object is separate from the topology. Topology is how you discretize. The geometry is where is it. And things like molecular dynamics, galaxy simulations, and collision detection. These are all spatial things. And Saeed have been telling me about stuff you guys have been doing on spatial stuff with triangle inequalities. And it's really exciting, and I would love to find some time in the future to look at how that geometry abstraction works together with the topology and the linear algebra, because sometimes either of these three is the best one, and moving between them can be important. For instance, evil mesh is a mesh together with the Lagrangian particles, together with the planets or particle in cell with Lagrangian particles moving around. So they have elements of different abstractions. And it's interesting to look at how you go between the abstractions. So to conclude, it's hard to write physical simulation codes because you have to optimize across these assemblies. And Simit helps because it has both extraction and a way to move between them in the same language. And it lets people write clean, short, and fun code. And the compiler produces fast code. And we used Simit last semester to teach computational fabrication at MIT. And it's available at that address. And the publication is also available at that address. The code is on GitHub, and it's under an MIT license. So it can be used commercially and for research. Thanks.
So all of these applications are not graph mutating, right?
That's true.
What about those? Like, for example, I remember back in grad school when we were looking at this problem of a crack in an airplane wing.
Yep.
Like it was just extending. So we had to do this fine refinement of the graph.
Regraphing, remeshing.
Yeah. So do you see that Simit going towards that direction?
So right now you can do that in C++. You can change the graph data structure. And then Simit will rebuild the indexes from scratch. So the indices of the graph, but also the indices of the matrices. I think it makes sense to bring those kind of things into the language. Because the language is graphs and linear algebra, but all our operations right now are in the linear algebra side. We want some operation on the graph side. And that could be mutating operations the way Gawa has shown that you can do. The important thing from the compiler side there is that you don't want to rebuild all the indices if you make a small cut where you just cut a few triangles apart. You don't want to rebuild everything. And that holds for the graph or the mesh, but it also holds for linear algebra. You don't want to rebuild the matrix index structures. But if you make them completely dynamic, like a hash map, you take a big cost when you actually compute. So there's a trade-off between computing with them, where you want them in place and compact, and changing them where you want them spread out. So I think what can make a lot of sense is a simple thing, which is just you have a CSR data structure for each matrix. And when additions and removals come in, you just put them in a diff list. Then you run your computation over the core CSR, and then you run some other computation at the end, because these operators are commutative, and associative, and distributive, which are important properties. And then when that diff list is some fraction of the size of your whole thing, you merge it in. And then you amortize that over all the... a more complicated data structure is something I've seen from the theory side, something called ordered file maintenance, where you can sort of trade locality for ease of insertion, but I doubt it'll work that well in practice. Yeah. Yes?
I was just curious, so in the mesh simulations, you're all using conjugate gradient. If you were to, do you have any choice over the solver that you use, like direct solvers versus iterative? Like,
yeah, that's my summer. So here.
So yeah, can you explain that? I've seen some other applications of Schur complement. So these functions that are being called are Simit library functions?
These are built-in functions. This is Cholesky factorization, so the matrix has to be symmetric.
But what confused me was this doesn't look like the code you were showing earlier. Those were like the shader equivalent little modules, functions. But this looks like C++.
Matlab.
Okay.
Well, most of Simit looks like Matlab. The computation part looks like Matlab. So you have to assemble your matrix, but once you assemble that, the real work begins, which is computing with it.
I see.
So here you also have linear algebra code.
I see.
So these things, this is a direct solver of a symmetric positive definite matrix.
I see.
This chol, which you factorize the matrix into L and L, and then you do a solve. These are built in right now, and I want to bring them into a language, because right now we can only implement basic linear algebra and control flow in the language. So it's Turing complete in one sense, but not in a useful way for these things. So we can implement CG, because that's just linear algebra, basic linear algebra. But these things have more complicated structure. So we want to start bringing in language primitives so we can implement that in the language. But right now we provide them as built-in functions that call out to eigen. Yeah, that doesn't make me happy to do that. That's a mission of defeat for a language person.
So have you thought, all of these linear algebra kernels operate over reals? Is it easy to extend to other semi-rings?
We support booleans, integers, reals, and complex.
Can I define my own?
The boolean, we want to extend it to other semi-rings, like tropical semi-rings, because the same hold. Yeah. And as long as it's a semi-ring, the sparsity of the matrices evolve in the same way because they require distribution and that stuff. I actually looked at stuff outside of semi-rings, but there the matrix structure goes completely crazy. Like you get things like if this is connected to one thing, it's connected to everything. So I don't think it makes sense to go outside of semi-rings, but we do want to extend the language to support other semi-rings like the min-max. And, yeah. Because then you can do graph algorithms, which is what you guys have been looking at.
That's what I was asking,
yeah, we've been talking a little bit to Jeremy Kapner at Lincoln Lab, he wrote a book about that and looked at that a bit. It's pretty cool stuff. But then, as you guys pointed out, sparse vectors start to matter. Which we can't do until we get the compiler theory implemented in Simit.
Have you covered like any of the graph applications, Convelas, thing?
No, but
it's not the same at all. But
no. So those things are equivalent to a linear algebra library in performance.
Right.
So we would be equivalent. The difference would be about, I'm guessing, the same as the difference between us and eigen. Because, so you still have to assemble your matrix. You don't start with a matrix. So that's where we would win.
Yeah.
But with the compiler theory that does fusion, we can also win in other parts. But of course, that compiler theory, we've only implemented in a library so that they can use it too.
Any more?
Thanks.
Thank you.